Okay, we're continuing with elementary number theory and methods of proof. Today we're going to be discussing indirect arguments, contradiction and contraposition. Indirect proofs are a little bit more roundabout. One kind of proof is indirect proof is argument by contradiction, and it's based on the fact that a statement is either true or false, but not both. So if you can show that the assumption that a given statement is not true leads logically to a contradiction or impossibility, then the assumption must be false, and hence the given statement must be true. This method of proof is also known as reductio ad absurdum, because it relies on reducing a given assumption to a absurdity or impossibility. Method of proof by contradiction. Suppose that the statement to be proved is false. That is, suppose that the negation of the statement is true. Show that this supposition leads logically to a contradiction, and therefore you can conclude that the statement to be proved is true. A little bit more roundabout. Got to deal with negations and all that sort of fun stuff. Used by proof of by contradiction to show that there is no greatest integer. Now, assume that there is a greatest integer, n, for all that all is greater than all other integers. N plus 1 is also an integer because 1 is an integer and n is an integer, so and addition is closed on integers, so n plus 1 exists. Therefore, your assumption that there is a maximum integer is false. Therefore, there is no greatest integer. So, for this proof, the certain property is the property of being the greatest integer. So prove that there is no object with this property. Begin by supposing the negation, that there is an object with this property. Suppose there is a greatest integer, call it big N. This means that big N is greater than or equal to n for every integer little n. Show that the supposition leads logically to a contradiction. Well, I just verbally explained it, that n plus 1 is an integer, and a big N can't be greater than that. So there is no greatest integer. Integers are an infinite set. The fact that no integer is both even and odd can also be deduced from the uniqueness part of the quotient remainder theorem. So theorem 472 is there is no integer that is both even and odd. One or the other, like true or false. Use proof by contradiction to show that the sum of any rational number and any irrational number is irrational. Well, let's see if I can remember how they do this here. So suppose you have R and S. Oops. I forgot to do that. Suppose you have R and S. R plus S. R is rational and S is irrational. That would mean that would be equal to, if you're assuming that it's rational, then R plus S equals some integer A over B. And since R is rational, R equals C over D. So S would equal to A over B minus C over D, solving for S. Okay? So S would be A D over minus C B over B D, right? But since A and D and A, B, C, and D are integers, this is an integer, and this is an integer, thereby making this a rational number, which contradicts the supposition that S is irrational. So the sum of two, a rational and a irrational number is irrational. Make sense? Kind of, sort of. You prove that this is an impossibility. So the negation of that is of the original state of the negation of what you're proving is true, which is the original statement that the sum of any rational number and any irrational number is irrational. So it goes a little bit more formally through it. Begin by supposing the negation of what you are trying to prove. If you take the negation incorrectly, the entire rest of the proof will be flawed. In this example, the statement to be proved can be written formally as, for all real numbers R and S, if R is rational and S is irrational, then R plus S is irrational. From this, you can see that the negation is, there exists a rational number R and an irrational number S, such that R plus S is rational. Follows that the starting point and what is to be shown are as follows. Suppose there is a rational number R and an irrational number S such that R plus S is rational. Show that this leads to a contradiction. To derive a contradiction, you need to understand what you are supposing. That there are numbers R and S such that R is rational and S is irrational, and R plus S is rational. By definition of rational and irrational, this means that there are convenient expressions that can be substituted for R and R plus S, but all you can say about S is that it cannot be written as a quotient of integers. So R is equal to A over B, R plus S is equal to C over D. Then substitute A over B for R, subtract A over B from both sides, and then do work a little algebraic magic here. And then now that both BC and minus AD and BD are integers, because their products and differences of integers are integers, and B times D is not equal to 0 by the zero product property, hence S can be expressed as a quotient of two integers with a non-zero denominator. And so S is rational, which contradicts the supposition that it is irrational. So sum of any rational number and any irrational number is irrational. Argument by contraposition. A second form of indirect argument by contraposition, is based on the logical equivalence between a statement and its contrapositive. You take the contrapositive of a statement, prove the contrapositive by direct proof, and conclude that the original statement is true. So, express the statement to be proved in the form of, for all x in D, if P of x, then Q of x. Rewrite the statement in the contrapositive form. For all x in D, if Q of x is false, then P of x is false. And then prove the contrapositive by direct proof. Suppose x is a particular element of D such that Q of x is false, and then show that P of x is false. Prove that for every integer n, if n is even, n squared is even. Or if n is squared is even, then n is even. First, form the contrapositive of the statement to be proved. The contrapositive is, for every integer n, if n is not even, then n squared is not even. By the quotient remainder theorem, with divisor equal to 2, any integer is either even or odd. And by theorem 4.72, no integer is both even and odd. So if an integer is not even, then it is odd. Thus, the contrapositive can be restated as, for every integer n, if n is odd, then n squared is odd. Then you would go and show that that is true in a direct proof method. Work it out algebraically. Relation between proof by contradiction and proof by contraposition. Observe that any proof by contraposition can be recast in the language of a proof by contradiction. In a proof by contraposition, the statement here is proved by giving the direct proof for the equivalent of in this form. To do this, you suppose you are given an arbitrary element of x of D such that not Q of x is true. You then show that not P of x is true. So you show not P of x from not Q of x. To rewrite this proof as a proof by contradiction, you can suppose that there is an x in D such that P of x is true and Q of x is false. You then follow the steps by proof by contraposition to deduce the statement not P of x. But not P of x is a contradiction to the supposition that P of x and not Q of x, because to contradict a conjunction of two statements, it is only necessary to contradict one of them. This process is illustrated here. You suppose that there exists an element x in D such that P of x and not Q of x. And you prove, and through a sequence of steps, you show that P of X is true and not P of X is true, which is a contradiction, and therefore the negation of this statement is true. The original statement is true. So proposition 474, for every integer n, if n squared is even, then n is even. Proof as a problem-solving tool. Direct proof, disproof by counterexample, proof by contradiction, and proof by contraposition are all tools that may be used to help determine whether statements are true or false. You might get a sense that a statement of this form here might be true. Explore further. Imagine elements in the domain that satisfy the hypothesis. Ask yourself, must they satisfy the conclusion? If you can see that the answer is yes in all cases, then the statement is true and your insight will form a basis for direct proof. If it's not clear whether the answer is yes, ask yourself whether elements of the domain satisfy the hypothesis and not the conclusion. If you find one, then the statement is false and you have a counterexample. On the other hand, if you are not successful in finding such elements, perhaps none exist. Maybe you can show that assuming the existence of elements in the domain that satisfy the hypothesis and not the conclusion lead logically to a contradiction. If so, then the given statement is true and you have a basis for a proof by contradiction. Alternatively, you can imagine elements of the domain for which the conclusion is false and ask whether such elements also fail to satisfy the hypothesis. Then you have the basis for a proof by contradiction or contraposition. And wrong one. Okay. Indirect argument examples, two famous theorems. When mathematics flourished at the time of the ancient Greeks, mathematicians believed that given any two line segments, let's say A and B, a certain length could be found so that segment A was exactly m units long and B was n units long for some integers m and n. Then the ratio of the lengths of A and B could be, it would be in the same proportion as the ratio of the letters of the integers m and n. Now it's easy to find a segment of the square root of 2 length, just take the diagonal of a unit square. By the Pythagorean theorem, the hypotenuse would be the square root of 2. If the belief of the ancient Greeks were correct, there would be integers m and n such that the diagonal and the side were proportional. And this would imply that c over 1 would equal to square root of 2 over 1. And that would equal m and n, m over n. But then square root of 2 would be the ratio of two integers, or in other words, square root of 2 would be rational. And we know it's not rational. So square root of 2 is irrational. Proof by contradiction that 1 plus 3 times the square root of 2 is irrational. The essence of the argument is the observation that 1 plus 3 times the square root of 2 could be written as the ratio of integers. Then so could the square root of 2. But by theorem 4.81, we know that to be impossible. So we know that 1 plus 3 square root of times the square root of 2 is irrational. Are there infinitely many prime numbers? No. We know what a prime number is. Is that set of numbers infinite? Or is there a largest prime number? Euclid figured this out, and a proof that the set of all prime numbers is infinite. Euclid's proof requires one additional fact we have not established. If a prime number divides an integer, then it does not divide the next successive integer. So for any integer a and any prime number p, if p divides a, then p does not divide a plus 1. And from this you can conclude that the infinitude of primes. When to use indirect proof? Examples in this section have not provided a definitive answer to the question of when to prove a statement directly or when to prove it indirectly. And many theorems can be proved either way. When both types are possible, indirect proofs have a tendency to be a little bit clumsier than direct proofs. In the absence of obvious clues suggesting indirect argument, try first to prove a statement directly. Then, if that does not succeed, look for a counterexample. If the counterexample method is unsuccessful, look for proof by contradiction or contraposition. So it's a contradiction and contraposition are basically methods of last resort. You don't want to necessarily start with those because those can be kind of clumsy and prone to errors, taking negations and such like that. And one more section, just for the fun of it, because we're moving right along here. Come on. Application, the handshake theorem. All right. Definition, the total degree of a graph is the sum of the degrees of all of the vertices in the graph. Find the degree of each vertex of the graph G shown below, and then find the total degree of the graph. So the degree of V1 is 1. Degree of V2 is 4. V3 is 2. And V4 is 3. Because that's how many edges attached to each vertex. So 1 plus 4, 5, 7, 10. So it's a total degree of 10. So, yeah. 1, 4, 2, and 3 equals 10. The handshake theorem. If G is any graph, then the sum of the degrees of all the vertices of G equals twice the number of edges of G. Specifically, it gives it more formally here, but the end result is the total degree of G is equal to 2 times the number of the edges, which leads to the corollary: the total degree of a graph is even, because it is 2 times some integer. So is graph A possible? With 4 vertices, each with degrees of 1, 1, 2, and 3? Is that possible? No. No, because it's an odd number of degrees. The total degree is 7 here, and that's an odd number. The degree of a graph is always going to be even. It's going to be 2 times some integer. But B would be possible. Yeah, and there's examples of how you could draw those graphs. Yeah. In any graph proposition, in any graph there's an even number of vertices of odd degree. So is there a graph with 10 vertices of degrees 1, 1, 2, 2, 2, 3, 4, 4, 4, and 6? No, it's odd. And you have an odd number of odd degrees: 1, 1, and 3. It'd have to be an even number of odd degrees to be an even number. So you can have the same result could be deduced by adding up the degrees, the total degrees, which is 29, which is odd. But proposition 493 gives a result without needing to perform this addition. Okay, now for a little bit more complex problem. At a meeting attended by a group of people, 4 people shook hands with 1 person, 6 people shook hands with 2 people, 2 people shook hands with 3 other people, and the rest shook hands with 4 other people. No 2 people shook hands with each other more than once, and a total of 23 handshakes occurred. How many people attended the meeting? Well, you have 4 shook hands with 1 other person, so you have 4 here. You have 4. You have 4. 3. I screwed up. Okay. Now, okay. 4 shook hands with 1 times 1 with 1 other person. 6 with 2. So 6 times 2. 2 times 3. and n times 4. All right, so we got 4, 12, and 6. So that's 4n plus 22 equals what? Not quite. 23 times 2. So 4n plus 22 equals 46. Because no, 23 handshakes. That's the it has to have 2 hands. So you two people, 2 endpoints on those are your edges of your graph, and this is the total degree. So it'd be 23 times 2, and then 4n equals what? 24. So n equals 6. So n equals 6. So plus 2 plus 6 plus 4 total is, what is that, 6, 12, 18. Am I counting? Is my basic math working right? Yeah, 18. Total would be 18. Sound about right? Okay. Total would be 18. The total number of people at the meeting. The 4, 6, and 2 people plus n. Make sense? Okay. So let's see if I did this right. Define the graph by letting each vertex represent a person at the meeting, letting each edge represent 1 handshake between 2 people. Total degree of the graph would be like we had there. So we had the 22 plus 4x, or n. Graph has 23 edges, and the total degree is twice the number of edges, so x is equal to 6, or n, that we did it, the way we did it. And then 6 people at the meeting shook hands with 4 other people, making a total of 18 people at the meeting. After all those years, I can still do basic math and algebra. It's amazing. But there are special kinds of graphs. A simple graph is a graph that does not have any loops or parallel edges. In a simple graph, one edge with endpoints v and w is denoted by the pair in curly braces. Draw simple graphs with 4 vertices, u, v, w, and x, and 2 edges, one of which is uv. Well, these are the resulting graphs that you could do. A complete graph is a simple graph with n vertices and exactly 1 edge connecting each pair of distinct vertices. Complete graphs for k 1, 2, 3, 4, and 5 can be drawn like so. You can go anywhere to any vertex from any other vertex. Prove that for any positive integer n, a complete graph on n vertices has n times n minus 1 over 2 edges. Well, suppose n is a positive integer. K is a complete graph on n vertices. Because each vertex of k sub n is connected by exactly one edge to each of the other n minus 1 vertices of kn, the degree of each vertex of k is n minus 1. So the total degree of k of n is the total number of vertices, n, times the degree of each vertex, n minus 1. By the handshake theorem, the total degree of k of n equals twice the number of its edges. So the total degree of is n, since the total degree is n times n minus 1, and that equals 2 times the number of edges of k of n. So dividing by 2 gives you the number of edges of k of n as n times n minus 1 over 2. Now, a complete bipartite graph is a simple graph whose vertices are divided into two distinct subsets. M vertices with V and N vertices in group W, in such a way that every vertex belongs to one of V or W, but no vertex belongs to both V and W. And there is exactly one edge from each vertex of V to each vertex of W, and there is no edge from one vertex of V to another vertex of V, and no edge from any one vertex of W to any other vertex of W. Okay, a lot of words. Pictures are worth 1,000 words. What does that mean? Fully connected groups. That's what that means. Now, you'll find these types of graphs in neural networks. The layers of neurons are connected by complete bipartite graphs. So, they do calculations, and there's, a lot of number crunching involved and all that sort of stuff. But as you increase the number of nodes or vertexes in each layer, the amount of computations go up and up and up very quickly, exponentially, as a matter of fact. Let's see here. You want to finish out the chapter? One more section? We got time, I think. We got a little less than half an hour. Or do you want to save that for Tuesday? Get it done? Get it done? Okay. Oh. See if we can get through this in half an hour. Come on. All right. Finally, application in algorithms. The word algorithm refers to a step-by-step method for performing some action. Some examples of algorithms in everyday life are food preparation recipes, directions for assembling things, sewing pattern instructions, instructions for filling out tax forms. Part of elementary school mathematics is devoted to learning algorithms for doing arithmetic, such as multi-digit addition and subtraction, long multiplication, and long division. An algorithmic language. The algorithmic language used in this book is kind of a pseudocode, combining elements of Python, C, C++, and ordinary but fairly precise English. We will use some of the formal constructs of computer languages, such as assignment statements, loops, and so forth, but we will ignore the more technical details, such as the requirement for explicit end-of-statement delimiters, range of integer values available on a particular installation, and that sort of thing. In high-level computer languages, the term variable is used to refer to a specific storage location in a computer's memory. To say that variable x has the value of 3 means that the memory location corresponding to x contains the number 3. A given storage location can only hold one value at a time. So if the variable is given a new value during program execution, then the old value is erased. The data type of a variable indicates the set in which the variable takes its value. Integers, real numbers, character strings, 0 or 1 for a Boolean variable, that sort of thing. An assignment statement gives a value to a variable. It has the form x : equals e. That particular syntax is, I want to say Fortran or Pascal, not one of the languages that they listed at the beginning. But that's how a different language does assignment, variable assignments. But when an assignment statement is executed, the expression e is evaluated using the current values of all variables in the expression, and then its value is placed in the memory location corresponding to x. The memory location corresponding to x is the pointers you all know and love in C++, I'm sure. Ordinarily, algorithm statements are executed one after another in the order in which they are written. Conditional statements allow the natural order to be overridden by the current values of program variables to determine which algorithm statement will be executed next. So, conditional statements are denoted by either if condition, then S statement 1 or else statement 2. The if-then structure is from BASIC, not from, again, from the languages they specified at the beginning. Where condition is a predicate involving an algorithm, the algorithm variables, where S and 1 and 2 are algorithm statements, or groups of algorithm statements. Generally use indentation to indicate that statements belong together as a unit. Using indentation to designate blocks is from Python. When ambiguity is possible, however, we may explicitly bind a group of statements together into a unit by preceding the group with the word do and following it with the words and do. So, The execution of if then else statement occurs like so. You've all had CS1 and 2, I believe, so you should know how if statements work. Consider the following algorithm statement or segments. If x is greater than 2, then y equals x plus 1, else x equals x minus 1, and y equals 3 times x. What is the value of y after the execution of these segments for the following value of x? If x is 5, x is greater than 2, so y would equal to 5 plus 1 or 6, so y would equal to 6. If x is 2, it's less than 2, so you do the else. X equals x minus 1, which would make it 1. Y would equal to 3 times 1, or 3. So it would be equal to 3 in the second case. Because value of x is 5 before execution, the guard condition x greater than 2 is true at the time it is evaluated. Hence, y would be equal to 6. Because x is 2 before execution, guard condition x greater than 2 is false. So the statement following the else is executed. Value of x is reduced to 1. And so y would then be equal to 3 because it would be 3 times x. 3 times 1. Didn't go over the B algorithm. Okay, there's the B. The while loop. The while loop has the form while the condition is true, execute these statements and go back to the beginning and check the condition again. And then you're familiar with the while loop in C++, I'm sure. So familiar with how they operate. This describes the execution. Pretty straightforward. Trace the execution of the following algorithm. I equals 1, s equals 0. I is less than or equal to 2. While that is true, s equals s plus I, and I equals I plus 1. So after the first iteration, s would be equal to 1, and then I would be equal to 2. The second iteration, I would be equal to 2, so s would then be equal to 3, and I would equal to 3. And then it would exit the while loop because I would be greater than 2. So, yeah, 1 and then 2, and then 3 and then 3, and passes to the loop. So at the end, I and S would both be equal to 3. I don't know if you learned about this in CS 1 or 2. the use of a trace table to track the values of variables through iterations and through various loops, whether it's a for loop or a while loop. But you can trace the iterations and determine outcomes. Again, we got the for next loop. For next is another basic construct. They don't use the keyword next in other languages that I'm aware of. The for loop is initial expression to final expression. That's the structure that BASIC uses, whereas C++ uses the initialized condition or initial state, condition, and increment format. But the end result is the same. So you do the variable is set to the value of the initial expression. Check to determine whether the value of the variable is less than or equal to the value of the final expression. If it's less than the final expression, then the statements in the body of the loop are executed in order. The variable is increased by 1 by the next keyword, and execution returns back to step 2. If the value of the variable is greater than the value of the final expression, then execution passes to the next algorithm statement following the loop. So, convert the for loop, the for next loop here, into a while loop. And what would the trace table look like? One to 4. While I is less than 5, or less than or equal to 4. X equals I squared, and I equals I plus 1. And then end the while loop. And the trace table would have I equaling 1, 2, 3, and 4. And X would be equal to 1, 4, 9, and 16. Ending at a value of 16. Yeah. Yeah. For X. A notation for algorithms. Express algorithms as subroutines that can be called upon by other algorithms as needed and used to transform a set of input variables with given values into a set of output variables with specific values. Output variables and their values are assumed to be returned to the calling algorithm. For example, the division algorithm specifies a procedure for taking any two positive integers as input and producing a quotient and a remainder of the division of one number by the output or the other as output. Whenever an algorithm requires such a computation, the algorithm can just call the division algorithm to do the job. Generally, we include the following information when describing algorithms formally. The name of the algorithm, together with its list of input and output variables, and a brief description of how the algorithm works. The input variable names labeled by data type, whether integer, real, number, whatever. The statements that make up the body of the algorithm, and the output variable names labeled by data type. The division algorithm. For an integer a and a positive integer d, the quotient remainder theorem guarantees the existence of integers q and r such that a equals dq plus r, and r is between 0 and d. So here is the division algorithm. A little bit involved, but pretty much it's repeated subtraction, while loop, r is equal to r minus d. And while r is greater than d, you subtract it and increase the quotient by 1. So trace the action of the algorithm on the input variables a, and a equals 19 and d equals 4. So repeated subtraction, you're subtracting from a repeatedly the 4 from the divisor, and your quotient counts up until your remainder is below the level of d. The Euclidean algorithm. The greatest common divisor of two integers, a and b, is the largest integer that divides both a and b. For example, the greatest common divisor of 12 and 30 is 6. The Euclidean algorithm provides a very efficient way to compute the greatest common divisor of two integers. All right. This gives a definition of the greatest common divisor character property. I think we can all are familiar with this. It's just a formal definition of it. Find the greatest common divisor of 72 and 63. If the definition of the greatest common divisor, GCD 00, is not allowed, why not? What would GCD 00 equal if it were found in the same way as the greatest common divisors for other pairs of numbers? Let's see here. Greatest common divisor of 72 and 63 would be 9, because 9 times 8 and 9 times 3 equals 72 and 63 respectively. Use the law of exponents on the second one. All right, let's see here. Suppose GCD 00 were defined to be the largest common factor that divides 0 and 0. Problem is that every positive integer divides 0, and there is no largest integer. So there is no largest common divisor. So there you go. If r is a positive integer, then GCD r of 0 equals r. If a and b are integers but not both 0, and if q and r are any integers such that a equals bq plus r, then the greatest common divisor is the greatest common divisor of b of r. So that's the Euclidean algorithm stating that. The Euclidean theorem stating that. So, Euclidean algorithm description. Let a and b be integers with a greater than b and b greater than or equal to 0. Find the greatest common divisor of a and b. First check to see whether or not b is equal to 0. If it is 0, then GCD a of a and b is a. If it isn't, then b is greater than 0, and the quotient remainder theorem can be used to divide a by b to obtain the quotient q and remainder r. So GCD, thus the problem of finding the greatest common divisor of a and b is reduced to the problem of finding the greatest common divisor of b and r by Lima 410. What makes this information useful is the fact that the larger number of the pair b and r is smaller than the larger number of the pair a and b. The reason is that the value of r found by the quotient remainder theorem satisfies r is less than b and greater than or equal to 0. And since by assuming b is less than a, we have 0 is less than or equal to r, which is less than b, which is less than a. Now just repeat the process again. Use b instead of a and r instead of b, and the repetitions are guaranteed to terminate eventually with r equals 0, because each new remainder is less than the previous one, and all are now negative. So you find you can find the greatest common divisor. Use the Euclidean algorithm to find GCD 330 and 156. Divide 330 by 156. You get 2 with a remainder of 18. So, if a and b are both integers but not 0, okay, yeah. We were just restating Lima 410 2. So divide 156 by 18. Get a quotient of 8 and a remainder of 12. And then do it again, 8 and 12. Quotient of 1, remainder of 6. Divide 18 by 12. And then 8, you get a remainder of 6. Divide 12 by 6. Get a quotient of 2 and remainder of 0. Therefore, you have the GCD of those 330 and 156 as being equal to 6, without having to do prime factorization or anything like that. The following is a version of the Euclidean algorithm written using formal algorithm notation. And you could write this down or copy it from the slide if you wish. I think finding greatest common divisors is part of cryptography or something like that. I think it's used in that with large numbers. Construct a trace table for the algorithm 410.2. And it gives you this. So and that will be it for chapter 4. I was planning on giving a quiz on chapter 4 on Thursday of next week, thinking that it would take that today and Tuesday to finish all the slides. I wasn't anticipating finishing the slides all in one day. So the choice is review session on Tuesday, or just take the day off on Tuesday and test and quiz on Thursday. Review session? Okay, we'll do a review session on Tuesday and then quiz on chapter 4 on Thursday. Have a good day, all.